Right, the last thing we're going to look at is a specific type of question. That's one where they ask us to form new polynomials using the roots of another polynomial. So if we're told that alpha, beta and gamma, etc., depending on how many roots the polynomial has, they're the roots of a particular one, but then it asks us to now create an equation which has roots. For example, they might say the reciprocals, 1 on alpha, 1 on beta, 1 on gamma. Now, we don't actually need to find alpha, beta and gamma to do it. What we do is we say, okay, I'm going to let y equal 1 on x. So you let y equal basically the form of the root. And so x is where the root is. So the root's on the bottom of the fraction. So y equals 1 on x. Make x the subject, and then substitute that back into the original polynomial. And that becomes the new one. But of course, you might have to rearrange it so it satisfies all the rules of the polynomial, because it can't have negative indices and things like that. So if it was some constant times alpha, some constant times beta, then I'd let y equal some constant times x. Again, rearrange x. If it was some constant alpha plus the constant, beta plus the constant, then I'd make x plus the constant. Again, rearrange it. Alpha squared, beta squared, gamma squared. Well, then I'll let y equal x squared. And then rearrange your x as y to the half and so on. So that's the basic idea. So here we go. We've got a cubic. Alpha, beta and gamma are the roots of this cubic. We're going to form an equation. Let's have a look at that reciprocal idea. So, all right, I'll let y equal 1 on x. X equals 1 on y. Substitute it in. There's our new equation. But, of course, that's not a polynomial. Mind you, technically, this question didn't ask for one, but normally it should say a polynomial equation. They are expecting polynomials. We don't have pronumerals in the bottom of the fraction in a polynomial. So I'll multiply everything by y cubed, and I'll get a new expression, and that is indeed a polynomial. So the solutions of this equation will be the reciprocals of the solution of our first equation. Okay, if it was alpha plus 1, beta plus 1, again, same idea. Let y equal x plus 1, so x is y minus 1. Substitute that in. Yes, that is a polynomial. Mind you, it looks a lot neater if we expand it all out and make it look like one. So we expand it out, group the like terms, and there's our new equation. So again, the solutions to this equation are one more than the solutions to the original equation. Now, straight away, because of the nature of the one I've just found here, I know one of the solutions to the original equation. Okay, I've got an answer of 1, I've got a factor of 0, and now I've got an answer of -1. It is one of those three. Okay, well, clearly we know a solution to our new equation is 0. I think we've all picked up on that. But these solutions are one more than the solution to the old equation, so therefore -1 must be a solution to the old equation. Okay, let's try the squared one. This one's a little bit more interesting. So we're going to let x equal y to the power of a half. Now, of course, we can't have fractional powers in a polynomial. So what we do is we split the polynomial into two parts. So everything that has a fractional power, I'll put on one side of the equation. Everything that doesn't, I'll put on the other. What I've also then done is I've factorised the bit that's left with the fractions, and of course we factorise by taking out the lowest power. So I've taken out y to the power of a half. Now if I square both sides, I will get rid of the fraction. Now it's important we moved every term over to the right hand side, because if I left it on the left hand side and squared it, then I'll create terms which are a combination of, say, the 2 and the y to the power of a half, and I'll still have a fractional power. So that's why we need to move everything that doesn't have a fractional power to the other side. All right, well now I can expand that one out, collect the terms, and we have our new polynomial for that particular one. Oh, by the way, some people worry about leaving it as y. It doesn't matter because it's still an equation. Notice the question didn't say find a new equations whose answers are x equals 1 over and so on. It just simply said find a new equation whose roots are this. So it doesn't matter what pronumeral I use, it's still going to have those roots. But if you prefer to change them to x's because for some reason you love having x in your equation, how about the reciprocal of the squares? Okay, so now I'm going to let x equal y to the power of minus a half. Sub that one in. Still same idea, everything with a fractional power I'll put on one side. But this time when I factorise, remember we've got negatives there. The lowest power is negative 3 on 2, not negative 1 on 2. So I'll pull that out. What I've done is basically, you'll notice that the minus 3 on 2, I've moved it to the other side and made it power of positive 3 on 2. In other words, I've divided by y to the power of minus 3 on 2, which basically turned it into a positive power. Now I'll square both sides, and we've got a polynomial. Of course, another way I could have done that is, having solved C, I could have said, now I'll find an equation which simply has the reciprocal of the roots of the equation in part C. That might have been easier. Find alpha squared plus beta squared plus gamma squared. Here's that classic question. It is talking about the original equation, of course, because remember alpha, beta and gamma are the roots of the original equation. So we could use the classical idea of, okay, sum of the roots 1 times squared minus 2 times the sum of the roots. And we end up with negative 2. But now we have an alternative way of doing that. Because in part C, we now have an equation whose roots are alpha squared, beta squared and gamma squared. So I could simply say it's the sum of the roots of that new equation. So it's simply b minus b on a, which sure enough turns out to be negative 2 as well. So it gives us, I guess, an alternative way. I'm not suggesting you would do it, but it's an alternative way of finding the sum of the roots squared. You could create a new polynomial that has the roots alpha squared, beta squared, gamma squared, and then simply say, okay, what's the sum of the roots of this new equation? Probably not the most efficient way of doing it, but it does work. However, having said that, if I had already found the equation in part C, and then like this one, they then say, find alpha squared plus beta squared plus gamma squared, it may well be easier to use the equation in part C because it's just minus b on a. Okay, so a few questions out of our Cambridge and several more out of Patel.